Welcome back to Easy Theory. Today we're going to be talking about a weird and quirky language, which I'm calling L here, and that is the set of all strings of the form a to some number, so some number of a's, followed by a pound sign, followed by some number of a's, followed by a pound sign, and so on. And then we end with another run of a's, such that k is at least 2, and all of the exponents here are different. There's a lot to say about this language, so let's get started. So there's a lot to prove about this language. We're going to be proving today that it is not regular, and then showing that it's not context-free. So the technique that we're going to be using for both is the pumping lemma. Pumping lemma for regular languages to show it's not regular, and the pumping lemma for context-free languages to show that it's not context-free. If you know something about regular and context-free languages, you'll realize that the second one implies the first one, that once we show it's not context-free, then we can show that it's not regular immediately because every regular language is context-free. But one of the interesting things about this language in particular is that the way that we're going to approach showing that it's not regular is totally divorced from the way that we'll show that it's not context-free, which means that there are many ways of approaching the exact same language. So let's show that this thing is not regular first. How we do so is we need to start with the fact that L is not regular. That's our claim. So let's start with claim. So I'm going to write the language back up here. Okay, so let's digest this language a little bit. The language is composed of all strings of the form, a bunch of A's, pound sign, bunch of A's, pound sign, and so on, where K is at least 2. Well, we need to know where the K is involved so that it makes sense. So K is right here. K is referring to the number of segments, in other words, the number of A's segments. And so when K is at least 2 here, that says we have at least 2 segments. In other words, there's at least 1 pound sign. A run of A's, 1 pound sign at least, and then a run of A's, then 1 more pound sign potentially, and then as more segments are added, then we will get a higher value of K. But as long as K is at least 2, then we're good. So let's do some examples. If I have the string A, pound sign A, then this string is in the language L because we have at least 2 segments, and the other condition here says that all of the I sub j's are different. So the I sub j's are the lengths of each of the segments of A's here. So this segment has 2 A's, and this one has length 1, and so therefore, since we have at least 2 segments, exactly 2 here, and their lengths are different, therefore this string is in our language L. But let's look at a string that is not in language L. If I have 2 segments where they have the exact same length on either side, then this string is not in L. So let's do a more complicated example. So if I have 1A, then 2 A's, and then 3 A's, and then back down to 1A, then these 2 segments have the exact same length, and then therefore this entire string is not in our language L. Let's do another one. Suppose that I had just pound sign. Well, that string is not in language L. That implies that this really is 2 segments, one on the left side and one on the right side, where both sides happen to be empty, and so therefore this string is not in L. And let's do one more. If I had pound sign with a single A, then this has also 2 sides, where this side is empty, and then this side has a single A. They are not the same length, and since we have 2 segments and their lengths are not the same, therefore the string is in L. It's good to do example strings like this to get a feeling for what the language feels like so that we can think of a strategy to show that a language is not regular. What is the feeling, the vibe that you can get from this language to get the fact that it's not regular? Well, it says here that all of the IJs are different, which says here that this is not the same as this, and I1's not the same as I3, I2 is not the same as I3, and so on. The fact that they have to be different implies that there's got to be some kind of counting mechanism which finite automata can't do. And so therefore that gives the vibe that this thing is not regular. But in order to show this, we need a full formal proof, so let's go ahead and do that. I'll start with a clean slate, and put down our claim, the thing that we're trying to prove, which is that L is not regular. You always need to start with a claim because you need to know what you're proving in order to actually prove it. So how do we start any pumping lemma proof? We need to assert the opposite, which is that L is regular, we assume that, and then derive some kind of contradiction at the end. And in every single pumping lemma case, we're going to derive a string that should be in the language, but isn't. So let's get started. Let's assume that, to the contrary, that L is in fact regular. Well, if it's regular, then there's some hypothetical out there DFA that corresponds to L. So let's do a hypothetical drawing here. Here's the DFA for L, and we have no idea what it looks like. And in fact, there's no possible way to know, because if we did, then it would be regular, but we're trying to show that it isn't. So clearly this thing doesn't exist, but this is just a thought experiment. So it's got some final states and whatnot, but we don't know anything about it. We do know that it has some number of states though. And so let's let P be the number of states in this fella. Why do we do that? Well, we want the number of states to have some known quantity, which is P here, because we need to feed in a string that's long enough to where we guarantee to repeat a state, so that we can make a longer string by going around the repeat segment, whatever it is, and then eventually get a string that is not in the language anymore. Now we need to choose a string that is in the language and length at least P. So we need to choose some string. And one tendency would be to pick a string like this. So a to the P, so that satisfies having length at least P. And we need at least two segments that have different length. So let's do P plus 1. These two strings have different length and it has at least two segments, so this string is good to go. However, this string will not work to show that this language is not regular. If you think about how pumping lemma works, you always will pump within the first P characters, which are these ones right here. So if we're going to be pumping within here, the pumped part can be any length between 1 and P based off of the pumping lemma conditions, which means that if we add more A's in to try to get these two to be the same, to try to generate a string that is not in here, in other words, these two have the same length, then that's not going to work. For one example, so suppose that the pumped segment in here has length exactly 2, or even higher than that. Well, there's no way to add 2 any number of times onto P, or subtract one instance of 2, in order to get it to be exactly P plus 1. Because 2 is even, this one's odd, and then therefore that's not going to work. So this string is not going to work. Well, then you may think, well, let's try P plus 2. Well, that's not going to work either for a similar reason, which is that we would have, for example, 3 A's over here. If we try to pump in another copy of 3 A's, then we're not going to have it be exactly 2 more A's than P, so that's not going to work either. Well, then you may think, okay, let's choose a much larger value over here. Let's do 2P. Well, that's not going to work either. So, for example, suppose just for the moment that P is equal to 7. Then that means we have 7 A's here and 14 A's over here. Then if we had some number that doesn't have anything in common with 7, so let's say 3, then if we're putting 3 A's into here over and over and over, there's no way to add 3 multiple times in order to get it to be equal to 14 from 7. And so this doesn't actually work. So there is one technique that does work, because we know that the length of the pumped piece in here must be between length 1 and length P. Then whatever we put over here must have the ability to add something to this in order to equal to this, which means it needs to be a multiple of every number between 1 and P. We need to pump some number of times in order for this side to be equal to this side. So one way of doing that is with the factorial function. So factorial is just the multiplication of all numbers between 1 and P, and then therefore every number between 1 and P divides p factorial. So we actually are not going to put p factorial here. We're going to put p plus p factorial because the number of a's that we add over here is going to equal this. And so it needs to start off with p, therefore we need the p plus here over here. So this is the string that we're going to pick. It clearly has length at least p because of this, has 2 segments, and this is not equal to this because p factorial is always at least 1. Well, what are we going to do here? Well, since we're dealing with showing that it's not regular, we know what all the decompositions are, which are going to entirely be over here, some number of a's over here. So let's look at all possible decompositions. So consider all decompositions of this string w that I made right here into the 3 pieces x, y, z, such that the length of x, y is at most p, and the length of y is at least 1. So those are all the decompositions. Well, what do we do with that? Well, since we know from these are the first 2 pieces, they have length at most p, therefore they are entirely within the first p characters, which are all a's here. So the x and the y portion are entirely a's, and the z part is the rest of the string. So from here, let's write down what the decompositions are. So we have x is equal to some number of a's. Let's call it alpha of them. And alpha, it can be anything at least 0. Y is also some number of a's. Let's call it beta. And since we know the length of y is at least 1, the beta number, which is the length of y, is at least 1. And z is the rest. Well, we started off with p a's. I should have changed these to red. So we have a to the p minus alpha minus beta here. That's the number of a's that are left for z to have, as well as it has all the rest. So it has the pound sign, and then a to all of the rest of the a's in the second segment. So we have p plus p factorial here. The question is, well, how many times do we pump y into the string such that the number of a's on the left side is equal to the number of a's on the right side? I don't know exactly what it is. Well, I've done this problem. I know what it is, but it's not immediately obvious what that is because this number is huge and this number is quite small in comparison. Like, think of it like 5, for instance. Then if this number is 5, then p is at least 5. And so this number is like 120 at the very least because that's 5 factorial. So this number can be huge comparatively to this. So let's think about it in a general context and then solve for the number of times to pump y later. So think about it generally and then solve for what the answer should be later. That's a common technique within CS theory sometimes. So I'm going to erase this. So we need to choose the number of times to pump, which is going to be something which we need to figure out. But let's figure out what x, y to the I, z even is. Well, that's I copies of y, and then 1 copy of x and z at the beginning and end. So that's going to be a to the alpha, and then I copies of this guy. So that's a to the I times beta. And then 1 copy of z. So that's a to the p minus alpha minus beta, p plus p factorial. Okay, so then let's scrunch all of these together. So we have a minus alpha here and a plus alpha here, so those cancel. And then we have a plus I times beta here, and then 1 beta going away, as well as a plus p here. So at the end of the day, we're going to have p plus I minus 1 times beta, because we have an I times beta here and a minus 1 beta here. Then pound sign, and then all of the rest of the a's over here. So the only way that this could be in the language L is if these numbers are different. We want to know when these two are different. So p plus I minus 1 times beta is not equal to, you can in this case check equal also, is not equal to that. So there is a plus p on both sides, so we can get rid of those. So we have to solve for I here. which is the number of times to pump, well, that is going to be dividing by beta, which we can do because beta is a number between 1 and p. So beta will always divide p factorial evenly. And so at the end of the day, the I that we need to choose, once we divide by beta and then add 1, is going to be 1 plus p factorial over beta. And it's important to note here that I is an integer, because if it wasn't, then this whole argument wouldn't work. But it is, because beta is a number between 1 and p factorial divides every number between 1 and p. So regardless of what beta is, this number is an integer, and then adding 1 obviously is also an integer. So we figured out the number of times to pump y, and if we do that number of times, then the left side is going to be equal to the right side. And so therefore that string is not in the language L, and then therefore this language is not regular. That's actually quite a complicated way to show that it's not regular. It's totally valid, but there's a completely other approach that we can also do. It's actually using something called a closure property. Key here to notice is that this problem is asking about difference. So if we can somehow invert that on its head, we can ask of when these numbers are the same or something like that. So let's figure out what we can do there. Well, if this guy was regular, if L really was regular, then the opposite question would also be regular, which means the complement. So if L were regular, then so would its complement. Then L bar would be also. But it's important to think about what this language is. So this is the set of all strings that are not of this form. So what are the things that could be different here? Well, it could be that at least 2 of the IJs are the same. So same format, but 2 of the counts are the same. We could have exactly 1 segment. We could have a completely different format than this. So like starting with a pound sign, although that is really technically the same format. So there are a number of things that can go wrong. But one way we can fix this is to use another closure property with regular languages, namely intersection. So intersection is very useful for when you want to impose a restriction on the language. So if you have a really complicated language, which is what L bar is, because it could be all sorts of weird things that doesn't follow this format, we can intersect that with another regular language that we do know something about. And so the strings that are in both must have the properties that are not this and the format that we like. This is really asking, when we talk about L bar, the mindset that we have is we want to check if 2 numbers are the same, which is a lot easier to do with pumping, because if you start with 2 numbers that are the same, it's easier to make them different than starting with 2 numbers and then making them exactly the same. So this is in our minds, although it's not exactly true, that all the strings in here have equal counts, because in principle you can have more counts, and if it's an L bar, you just need 2 of them to be the same, not all of them to be the same. So what we can do is intersect that with the language of all strings that have exactly 2 segments, and then therefore, if it's an L bar, those 2 segments have to be the same. Here's what we're going to do. We're going to consider a language, L bar, intersect A star, pound sign A star. Then this language right here is the set of all strings that are not in this guy, so must have something to do with IJs being the same or something else entirely. And you must have exactly 2 segments here. So if you have exactly 2 segments, the only way that a string in this can be in here and in here is if you have exactly 2 segments and the 2 segments have the same length. We actually know something about this language. What is it? It's the set of all strings of the form a to the n, pound sign a to the n. Notice that we have the same exponent in both, so they must have the same length, where n is at least 0. This one is a much easier language to deal with because we have exactly the same length. And so the string that we would pick would be a to the p, pound sign a to the p, because it needs to be in here. And we would only be pumping in here, and all we need to do is pump up once to make more a's over here, and we wouldn't be able to touch them over here. And so therefore, that's a much easier way to show that this language is not regular. A completely different way to show it's not regular, but also totally valid. Pretty cool. Now, let's show that it's not context-free. So here's the problem in showing that this language is not context-free. We can't use the same string as before. Both the closure property as well as the p factorial trick. Why? Because in both cases, we picked a string that had some number of a's, a pound sign, some number of a's. So exactly 2 segments. But the difference with the context-free pumping lemma is that we can pump anywhere. So remember, in the context-free pumping lemma, we have 5 pieces where 2 of the pieces will be pumped into the string. So it's not just 1 piece within 3, it's 2 pieces within 5. And those 2 pieces can be anywhere in the string. So regular says that they need to be pumped within the first p characters, whereas the context-free one says you can pump anywhere that you want as long as you're within a p length window. For instance, in this string right here, so let's say there's like p characters at the beginning here and some other number here, then what we can do is we can pump a single a over here, and then the second piece that's pumped is pumped over there. And no matter what we do, if we pump once, for instance, we increase the number of a's over here by 1, but also increase them over here by 1. And that's not going to help us because we need to have these numbers on the left and right side to be different to start with in the first place. And if we increase them by the same amount when we pump, then that's not going to cause one side to become the other because they increase by the same amount. That's not going to work. And so if we're going to show that this is not context-free, then we need some way to have a bunch of segments potentially. There's a bit of a problem there because what are those segments going to be? And in order to comply with this, they need to all be different in order to be chosen as a string to work with in the very first place. The key is to think about, what does pumping really do? So imagine that we have like a run of a's here. So we have some number of a's here. Well, whatever it is, let's say it's a very large number of a's. What we can do is, if we have both of the pieces that are pumped in here, then the conditions of what they are actually very helpful. So these pieces are called v and y, and there's a middle piece called x that is not being pumped. And the conditions state that vxy's length is at most p, and the length of v and y together, so without the middle piece, is at least 1. In other words, that v is not empty or y is not empty. It can't be the case that both are empty. This condition says here that the maximum number of things we could ever insert when we pump once is at most p. Or if we pump down, then the max we can delete is at most p. Which is kind of interesting. So like if we have, for example, p is equal to 5, and we had some run of, let's say, 7 a's, then what that says is that the vxy portion has at most 5 a's, but those 5 a's could be anywhere. So let's say there are 4 a's here. Then that means that if we pump one copy of those a's in, then that means, well, we started off with 7, and we're going to now have 11. And so that gives us some intuition as to what's going to happen. So if we have a gigantic number of segments, all of different lengths, and then we're at some random length in the center, so like some segment in the middle, then if we pump up once, assuming we have enough segments, we're going to jump to some other segment because we have stored all of the possible lengths between something and something. So that's actually the idea to have when approaching this problem, is that since we can pump anywhere, we can only locally pump within the string at a tiny portion. And so if we pump within that, then we're going to land at some other portion which we have no control over. Whereas when we had 2 segments, we had control over both. And so that gives us some intuition as to what the segment should be. Because this condition says that the vxy portion has length at most p. And so therefore, the maximum number of segments that we should ever touch, we should hope to be very small. We don't want to touch a bunch of segments to all muck with them in order to not guarantee that we'll have two segments that are the same. So the technique among many, there are many ways of attacking this, is to make all the segments of length at least p. So let's think about how that's going to work. Let's start off with the proof. Well, start off with the claim. L is not a CFL, so not a context-free language. So let's prove it. So let's assume that L is in fact a CFL. Then that means that there is some pumping length for L. Let's call it P. So let P be the pumping length for L. Of course, I don't know what this number is because we're trying to show that it doesn't exist, but assume that we have some number here. What we need to choose is to now choose a string like the regular version that is in the language and length at least p. But according to the strategy that we had, which is to make all the segments of length at least p and make a ton of segments. Well, let's think about what that is. Well, the first segment's got to be length at least p for that reason. But I want all the segments, one more than this one, then one more than that. So a length of p plus 1 here, then p plus 2 here, then p plus 3 here. But the question is, how far up do we go? The key is to notice that if we pump up ones, then we can insert at most p things. And so therefore, if we're somewhere in the middle, so let's say like p times 1.5 or something, even though that might not be an integer, but a thought experiment. So if we're here, then if we pump down or up, then we could in principle insert or add PAs. So if we're here and we tried to pump down, then that means we could be all the way down to P over 2, which is less than this. Similarly, if we pumped up, then we could in principle go all the way to 2.5 times P. And so you may think, okay, we need to go up to 2.5 times P. Well, now we're actually home free, because if we're this high, then if we pump down, then that means that we'll be down to, at most, 1.5 times P, which is going to be some length in here. But then the question is, well, how high do we need to go? Well, what is the minimum here that we can be guaranteed to be fine if we pump down? Well, that's 2P. So if we had P times 2 here, if we pump down, then this will be, at the worst possible, equal to this segment, and then potentially some other segment in here. It actually will be some other segment here. But then the question is, well, what if we had the segment right before this, which is a to the 2p minus 1? Well, if we pump down here, then we could end up with p minus 1 a's here, which is not ideal. So we would want to pump up with this. But if we did that, then we would need 3p minus 1 a's. So the strategy is to start off with PA's and then work your way up until you get to 3p a's. That reasoning was kind of convoluted, I totally understand. There are other ways to solve this problem. This is not the only way. In fact, you can use a shorter string than this. This is just a logical way that I use to solve problems like this. So we have p plus 1, then we have p plus 2, and then so on up to 3p minus 1, a to the 3p. Be aware though that since we're dealing with context-free, we can in principle be pumping anywhere in the string. We don't have to be uniformly within a section of a's here. So in principle, we could have some of the pound signs. Well, in this case, we can only have one pound sign because it's impossible to have two, since each pair of pound signs here is separated by at least PA's, in fact more than that. So we can have at most one pound sign here. But in principle, we can have some of the pump P's be in the A portion, say in this segment, and then some of it be in this segment here. That's totally possible. So let's look at all possible decompositions and see what happens. What are all the possible decompositions of W, let's make a better W here, into those 5 pieces, such that the length of Vxy is at most 1, and the length of Vy is at least 1. In other words, V and Y, one of them is not empty. Well, suppose that they're within a single segment here. Then we're actually home free because we have discussed the strategy of how to pump here. If we're in our segment that is with at most 2p, then we pump up, which will have us be within 2p and 3p. And if we are within 2p and 3p, we pump down to I equals 0. So the first case, which is case 1, is going to be v and y are in a single segment. So we have to be a little bit careful here to say what the segment actually is. So let's say that it's a to the m, some number m here. Well, if m is at most 2p, then we can pump up to I equals 2. So if m is at most 2p, then pump up to I equals 2. Otherwise, which means that it's bigger than 2p, pump down to I equals 0. And that's the reason that we said before. That is not all decompositions, but this is one important case. Another case is, suppose that we have a pound sign somewhere. Then we actually might be in trouble, or it sounds like we would be in trouble. Because suppose that one of the segments is empty. So let's say like v is empty, and then y is the non-empty one. And then let's say y is that guy. Well, if that's the case, and we pumped up to I equals 2, then that means that we're going to have pound sign, and the empty string is not in there. It's not one of these because these have length at least p. But the good thing is that we can choose another value of I. So imagine that we pumped y in twice to I equals 3. Well, then that means that we're going to have pound sign. But that means we have the empty string twice. That's not the only possible case. Well, for example, y could have some of the a's here and some of the a's here. But it turns out that you will always have the same segment when you pump up to I equals 3. So let's prove that. So case 2, let's say that v and y contain a pound sign. Well, it can't be that both of them contain it because that would imply that you have 2 pound signs, but that's impossible because of how they're structured here. So let's assume without loss of generality that v has the pound sign. It'll be the exact same reasoning if y does because we pump both of them at the same time. So let's suppose without loss of generality, so that's what w log stands for, v has the pound sign. Then we're going to pump up the jam to I equals 3. The thing is that what can v have? Well, v can't have another pound sign. So the worst that it could possibly have is some a's on the left side and some a's on the right side. So let's say that v is equal to some number of a's on the left side. So let's say it's r on the left side. And it could be 0. And s on the right side. Again, these could be 0. But let's suppose that it looks like this. Then let's suppose that we pump up to I equals 3. Well, then that means we have 3 copies of v here. So that would be v, v, v. And so let's just write down this string 3 times because they're pumped in place. AR pound sign AS. So that's 1 copy of v. Then another copy of v. And then another copy of v. One thing that you might notice here is that we have the same segment twice. Isn't that kind of cool? Where that these strings, which might be totally smaller than these, and that's in fact almost certainly going to be the case, they just happen to pop out to be exactly the same. Isn't that awesome? So this case will work because we can always induce another one. In fact, if you pump up to higher, obviously we're going to have more of these by induction. But anyway, so that works. But there's yet another case, which is suppose that they do not contain a pound sign. It is not case 1. That means that the v is on one of the segments and then y is on the next segment. So let's think about what can happen there. And that is in fact the only other possible case, because if it's not within one segment and it doesn't have the pound sign, it can be in at most 2 segments because it can't have 3 segments because all of the segments have length at least p. So let's do case 3 here. So that would be v and y are in different segments. So let's draw a little picture of this. So we have some number of A's here, pound sign, some number of A's. Then the V portion is over here somewhere, and then the Y portion is over here. Let's think about what happens. Well, notice that the length of this segment is exactly one less than the length of this segment because of how we structured the string, even though I erased it. So let's say that this has length M here, and then this one must have length M plus 1 here. Y must be in the bigger segment, V must be in the smaller segment. It could be that this is the shortest segment, that could be the case, or this one is the largest segment, so we need to be a little bit careful there. But suppose that V is not in the smallest segment. Let's think about what can happen here. Well, if we pump up, then it could be that this is a very late segment, so like close to the 3p limit that we had. So let's adjust expectations. Let's say that V's length is 1. And we are in an early segment. So that means M is at most 2p. Then what we're going to do is we're going to pump up to I equals 3. And the reason we do that is that it could be that Y is empty. And that V is not empty. So if we pumped up once, then this segment would increase by 1 to this guy, and that would be equal. But suppose that Y's length is not 1, then that means that this guy is going to increase when we pump up. This one's also going to increase, but only by 1. And so Y is going to go up, and this guy is going to hit a hole that's here, and so therefore they might not be exactly the same. So you can actually guarantee that Y is going to hit something because of this, but anyway. So we're going to pump up to I equals 3. And that's going to skip the hole that is going to be left by Y potentially. But if we're in a late segment, so like we're near the end, then we're going to pump down. Because if we pump down here, then this guy is going to hit one of the earlier segments on the left side. It doesn't matter what this one does because it's in a larger segment. So if this is the case and M is bigger than 2p, pump down to I equals 0. Now let's think about, well, what if V's length is not 1? Well, we can actually do the exact same thing as we did in case 1. We can just think about, well, if this guy is in an early segment, we can just pump up because that's going to hit some other segment that is past Y. It doesn't matter what Y does, it's going to hit some other segment that's past Y. And if it is in a late segment, so above 2p, we can pump down just like we did in case 1. Otherwise, pump as in case 1. Because case 1, we dealt with V specifically, and so we just deal with whatever case V is in. That is this language. It is a really interesting language that allows you to think really deeply about how to show that it's not regular, first of all. And showing context-free is in a totally different approach because of the conditions imposed by the pumping lemma for context-free. And so I hope that was interesting, and hopefully this gives you some insight into proving other languages to be not regular or not context-free. Thanks for watching.